at physics paper 2. We'll be looking at physics paper 2, and we will try as much as possible to run through this paper and give it a value, okay? So let's go through this paper 2 quickly and see what we have in front of us as fast as we can. This is May-June 2021. This is May-June 2021 paper 2-1. Okay, so without much ado, let's begin the questions. Question number 1, the diagram shows a stone of irregular shape. Irregular shape means it doesn't have specific dimensions, so it's almost difficult to calculate the volume, except that if you want to do the volume, except that you have to maybe put it in a measuring cylinder where you already have some water. Now, which properties of the stone can be found by lowering it into a measuring cylinder half filled with water? Okay, that's volume, right? That would be the volume. That would be the volume. I just mentioned it. I didn't even know they were going there. So that would be the volume. Okay, the property that will enable you to calculate the cylinder, that will enable you to get the property of the stone that you can do by lowering it to the measuring cylinder half filled with water is the volume. So number 1 is the volume. Now we go to number 2. Number 2, which row describes speed and velocity? Which row? Speed is scalar, velocity is a vector. So A is wrong. Scalar, vector. Yeah, B is correct. Vector, scalar, no. Vector, vector, no. So speed is scalar and velocity is a vector. Speed is scalar and velocity is vector. So number 2 is a B. Now we go to question number 3. Question number 3, 4 balls with different masses are dropped from the height. 4 balls with different masses are dropped from the height shown. Air resistance may be ignored. So you may ignore the air resistance. You may ignore the air resistance. Okay? Which ball has the smallest average speed? Which ball has the smallest average speed? Okay. So which ball has the smallest average? Sorry, my battery is low. I'm trying to plug it. Okay, now let's move on. Which ball has the smallest average speed? Air resistance may be ignored, right? They say which ball has the smallest average speed. Okay, now we have A, we have the mass, we have the distance. Okay, speed, what's the relationship with speed, mass, and distance? A mass of 4 kilograms moves a distance of 1 meter. So, what's the work done is force times distance. Force can be calculated as the weight. So, if you want work done, you say force times distance. Force times distance. But in this case, they're asking of the speed. They say which ball has the smallest average speed. Okay, so we can see this is 3 kilograms and a distance of 2 meters. This is 2 kilograms, a distance of 3 meters. This is 1 kilogram, a distance of 4 meters. So you say which of the ball has the smallest average speed? Average speed is total distance over time taking, right? Average speed is total distance over time taking. But these questions do not have time taking. But one thing we can calculate is the work done by each of the ball. Okay, the work done. The work done by this will be 40 times 1, which is 40. For the first one, this one will be 40. The work done, 40 Newton meter. This one will be 30 times 2, which is 60. Because it will be times 10, you know. To get the weight, you must say, or to get the force, you must say times 10. Okay, so 30 times 2, you get 60 here. This one will be 20. 2 times 10, you get 20 for the weight. Then times 3, to get the work done, 20 times 3, you also get 60 for the work done. This one you get 1 times 10, you get 10 times 1, you get 40 also. Okay, but this one will move a longer distance. So the one with the which ball has the smallest average speed will be ball A. Okay, this one will have the smallest average speed because it worked. Although the work done is 40 Newton meter, but the ball is just moving through a distance of 1 meter. So it will have the smallest speed. Okay, we have the smallest speed. Now let's move to the next question. Question number 4. Okay, question 4. We say an object of mass 2 kg is taken from the earth, where the gravitational field strength is approximately 10 Newton per kg. It's taken from the earth to the moon, right? Where in the moon, the gravitational field strength is just 1.6 Newton per kg. Which row is correct? So the weight of the ball on earth. On earth, the mass, if you want weight is mass times gravity. Mass times gravity, mg. So weight is mg. So on earth, g is what? So the mass of the ball, an object of mass 2 kg. So the mass is 2. So on earth, 2 times, what's the gravity? 2 times 10, which is 20. So on earth, we get 20 Newton. Okay, we get 20 Newton. So on earth, the weight is 20 Newton. In the moon, the weight will be what? The weight will be 2 times 1.6. 2 times 1.6 will be 3.2, right? 2 times 1.6 will be 3.2. So we got to look for option that has this. In the moon, 3.2 Newton. That will be the weight of the ball or of the object. And so the answer is D. So see here, on earth this is earth. Here's earth, and here's moon. So 20 Newton for earth and 3.2 Newton for moon. So we'll move on to the next one quickly. Say a mass of an empty flask is 34 gram. Empty flask is 34 gram. Okay, the flask, as you've not put anything, you've not put water. The mass itself is the flask itself is 34 gram. Now the volume of liquid added to the flask is 20 centimeter cube. Now the total mass of the flask and the liquid is 50 gram. So which means mass and flask and liquid is 50. Okay, we have flask. Total is 50 gram. So if you want only the substance that has been added, if you want the mass of the substance, you go to subtract the total mass of flask and liquid. Okay, you want the mass of liquid now. Let's say we want the mass of the liquid, because they might ask us to calculate the density of the liquid. So to get the density of the liquid, you have to know the mass of liquid, right? So mass of liquid is equal to the 50, which is, you remember 50 is for what? The flask and the liquid, both. Okay, the 50 gram is for the empty mass flask and the liquid added to it. Everything total up to 50 gram. But ordinary flask is 34 gram. So if you want only mass of liquid, you say the total, which is 50, minus the empty mass of the flask. So this minus this, what you get? 16, right? You get 16 gram. So this one we get 16 gram as the mass of the liquid. Remember, they've told us the volume of the liquid. They said the volume of the liquid is what? 20 centimeter. So volume, so I just say V of liquid, volume of liquid is what? Volume of liquid is 20 centimeter cube. 20 centimeter cube. So calculate the density. This density will be in gram per centimeter cube. So density, which is rho, you can use this symbol, rho, for density, equals mass over volume. Equals mass of liquid over volume of liquid. Is equal to mass of liquid over the volume of liquid. So mass of liquid is what? 16 gram. 16 divided by 20, what do we get? 0.8, right? It's 0.80. Because this, if you divide this, you get 4 over 5. 4 over 5 is 0.8. So 0.80. Okay? 0.80 gram. Remember, it's going to be gram per centimeter cube. Okay? Not just 0.80 gram, but you must know the unit. 0.80 gram per. So our answer is what? A. Our answer is A. Is that okay? Now we go to the next question. It said the extension load graph for spring is shown. Now the unstretched length of the spring is 70 centimeter. So the stretched length of the spring is 70 centimeter. You know, right? So that would be our benchmark. That would be our benchmark. That would be our benchmark. The stretched length of the spring is 70 centimeter. Now you say when an object is suspended from the spring, the length of the spring is 19. When object is added to the spring, it extended. The length becomes 19.2. So we can calculate our extension. Extension x is the new length, length new minus length original minus our original length. So which means this is 90.2 minus 17. Was it 17? Yes, minus 17. 90.2. So you get 2.2, right? So this will give us 2.2. So our extension is 2.2 centimeter. So we get an extension of 2.2 centimeter. Remember, we want to calculate Hooke's law. We want to use Hooke's law. You say now, what is the weight of the object? What's the weight of the object? Remember, according to Hooke's law, the weight, which is called the force, okay, is directly proportional to extension produced. This is equals to KE. K is the spring constant. K is the spring constant. We can use E or we can use X. Some textbook, they use X for extension. Some use E for extension. So it doesn't matter. Okay? So if they are asking for the weight, the only challenge you have first, what you have to do is to calculate the spring constant from the graph. Right? Calculate the spring constant. So we can choose any force. But we choose the one that is relatively good. We already know the extension. Extension is 2.2. But we don't know the spring constant. To find spring constant, you know K is F over E. K is what? F over X. Make K the subject, you get F over X. So if your X is 2.2, if you can locate 2.2 here, this 2.1, 2.2, right? Oh, this extension has this. Go to extension has this, where is 2.2, 2.1, 2.2. Now let's find the corresponding force, the load. So you go to trace, you follow this to this one. We go to follow it. Okay, we go to follow it and trace it to the line graph. Trace it to the line graph. So it touched here, right? So if you bring here, the force is what? 3 Newton. If you bring it down, the force will be, don't mind my wrong drawing, okay? Okay, the force is 3 Newton, right? So you just put 3 divided by 2.2. 3 divided by 2.2 so that we can get our spring constant, the value of the spring constant. So 3 divided by 2.2, what do we get? We get 1.36. 1.3636. So we just say approximately 1.36. Okay, so this our spring constant is 1.36. Okay, so we bring it here and we solve. What is the weight? Weight will give us, obviously weight will give us 3. We don't need to even, so from the graph we can just tell the answer, right? The weight is 3. We don't even need to solve, because if you solve again, just take your extension, trace it here, trace it down, you get the weight. You get the weight. Weight is 3 newtons. So you just come here. No need to solve again. Because if you solve, you still get the same thing. If you come here and put the extension, you got 1.36 multiplied by 2.2, you get 3, approximately 3. So no need to solve. Just come, trace the extension to the graph, trace it down, you get the weight, which is called the force or load. You can use the word load or force or weight. It's all the same thing. So we'll move to the next one. We move to question number 7. Question number 7. Let's quickly take a look at it. We say a cat has a mass of 10 kg. So we know they're giving us mass. This is mass. A mass of 10 kg. A boy pushes on the cat horizontally with a force of horizontally. A cat has a mass of 10 kg and a boy pushes on the cat horizontally with a force of 15 Newton. The cat accelerates at, so we will give you acceleration. We give you A. Acceleration is A, right? And then we know the mass, which means we can calculate the force or weight of the cat. So 10 times 10, this will be 100, the weight. Okay, and a boy pushes the cat horizontally with a force of 50 Newton. You're pushing it with a force of 50 Newton, right? The cat accelerates at this. What is the frictional force acting on the cat? What is the frictional force that is acting on the cat? So you remember force equal to MA, right? Force equal to MA. The frictional force is the coefficient, okay, of the MA. So if we have here, we have the weight of the object to be mass mg, right? So we have 10 times 10, which gives us 100 as the weight. Which gives us 100 as the weight. 100 Newton. Okay, so the weight is 100 Newton, and a force, there's an acceleration of 0.5 or 0.50. Okay, so let's substitute it to this formula. The weight, which is 100, is equal to this coefficient of friction multiplied by, no, the weight is 100, so 100 is here. Here is 50. So this is 50 over 100, right, which gives us 0.5. So this 0.5 is used to calculate the overall force. The frictional force. So we say our acceleration, we did put the value of acceleration. We did put the value of our acceleration. Our acceleration was 0.5. So we have 0.5 here times the mass, which is 10. What do you get? That's 5, right? Okay, so that's 5. So to get the frictional force that was acting on the object, remember the boy pushes, you get this, your F equal to MA. This is your F equal to MA formula. So the mass, this mass, and this is the acceleration of the object, 0.5. Now this acceleration of the object, multiplied by this, you get 5. Now after getting to this 5, you subtract it from the original force that was pushing the object. You get the frictional force that is acting. So frictional force, the frictional force, force of friction, is equal to the force that was pushing the object minus the 5 Newton force we just calculated. 15 minus the 5 Newton force that we just calculated. So this will give us 45 Newton. This will give us 45 Newton. Okay? So no need to do this because they already gave us this. Sorry, I forgot they already gave us this one. So there was no need for this calculation because they already told us that is 0.5. So there was no need for this. What we just need to do is to substitute mass times acceleration. 10 times 0.5, you get 5. Subtract it from the main force that was pushing it, you get your frictional force D. Okay, so this question is D. Now we move to question 8. What's our question 8? Question 8 says that a ball has a mass of 2 kg. A ball has a mass of 2 kg and the ball approaches a wall at a speed of 3 meters per second and rebounds at a speed of 1 meter per second. Okay, let's take a look at this question again. A ball has a mass of 2 kg, so this is the mass of the ball, and the ball approaches a wall at a speed of this, so there's a momentum. The ball approaches a wall at a speed of 3 meters. So it has a mass of 2, so we can calculate the momentum of the ball as it was going this way. So the ball was going this way, right? So the momentum before collision, before it hit the wall, is mass times velocity, or mass times speed. The mass times speed. So the momentum is mass times speed, which is 2 kg times the speed is 3 before the ball collides. So the momentum before collision is 6. The momentum of the ball before collision is 6 kilogram meter per second. 6 kilogram meter per second. That's the momentum of the ball before collision, before it hits the wall. So, and it rebounds at a speed of this. So after it collided, it started going in the opposite direction. So what's the momentum after collision? So momentum after collision will be 2. Momentum after collision, this is before. You know, law of conservation of momentum says the total momentum before collision equals to the total momentum after collision. So the momentum, this is before, so we can write before, capital B. Then momentum after collision is equal to the mass is 2, right? The mass is 2, and the speed is what? See, after he hit the ball, he start going backward, going in the opposite direction with 1 meter per second. So the speed is 1 meter per second. So we get 2. 2 times 1, we get 2. We get 2, right? Now the law of conservation of momentum says that the total momentum before collision is equal to total momentum after collision. Okay, for momentum to be at equilibrium, to be conserved, the total momentum before collision of the ball equals to the total momentum. So what is the impulse on the wall? Now they are asking for the impulse. Remember, impulse is, what is the impulse on the wall? Okay, impulse is force times time. Okay, impulse is force times time. But you can see in the question there was no time. If there is no time, no problem. Impulse is also equal to change of momentum. Change of momentum. Impulse is equal to change of momentum. Since the question is asking us for, the question is not even asking us the total momentum. So it's equal to change of momentum. So what's the speed? You have the mass, which is 2 kg. What's the speed? 1. Minus. Why is it minus? Because opposite direction, right? Minus 3. So why is it like this? 1 opposite, there's already negative in the formula, but because this one is to the right, the other one is to the left, so another minus. So you must introduce a second minus. So 1, this will be equal to 2 multiplied by 4. This will be equal to 2 multiplied by 4. Why? Why did I do that? Or why did we do that? We did that because this speed is going this way, this other one is going. From the formula, you already have 1 minus. But because they are in opposite direction, you must introduce another minus. They are not going in the same direction. If they were going in the same direction, it will just be 1 minus 3. Since they are in opposite direction, this is how the second minus came. If you like, you put a small bracket within this one to show that it's opposite direction to 1. And this first minus is from the formula. Okay, change of momentum. because this change of momentum is equal to impulse. It's also the formula for calculating impulse. Okay, impulse is either you use ft, if there's no time in the question, if there's no time, you use the change of momentum to calculate impulse, which is m equal into v minus u. So this 2 times 4 gives us 8. So you get 8 Newton second. 8 Newton second. Remember, impulse, the unit is Newton second or kilogram meter per second. So our answer is D for this question. Our answer is D. Okay, they were not looking for the change in momentum, but it's okay, we've done this. We did this before we read the last part of straw of the question, and we then realized, see, they put 8 Newton here, they put 8 Newton second. So if some student may mistakenly go and circle this one, they are asking for impulse, they are not asking for force. If they are asking for force, then it's 8, it will be in Newton. But they are asking for impulse. Impulse, the unit is, so they want to, here they are testing 2 things. They want to know whether you know units of simple measurement. Now let's go to question 9. Question 9 says that which situation involves no work be done and no energy be transferred? Which situation involves no work be done, no work is done, and no energy is being transferred? A car skidding to a stop on a road. No, work is done, right? You're trying to stop, and energy is transferred to the brake. A crane lifting a load, work is done. When you lift a load, work is done, because this is a vertical work done, actually. A heavy load hanging from a strong bar. It's just hanging, no work is done, right? If you're hanging, no work is done and no energy is being transferred. It's just a gravitational potential energy. Work is not done, no energy is transferred. A student dragging a big box with a rough floor. A big box over a rough floor. If you are dragging a box on the rough floor, horizontal work is being done. So that's not the answer. Okay, we move to question 10. So we are trying to see if we can a bit go faster today. Okay, for this one. A student suggests that there are several ways of transferring energy to a small stationary block of iron on a smooth table. He makes the following suggestions. So a student suggests that there are several ways of transferring energy to a small stationary block of iron on a smooth table. He makes the following suggestion. He makes the following suggestions. Now let's see. He says heat it. Okay, you want to transfer energy to a small stationary block of iron on a smooth table. So you heat it, yes. Shine light on it. Pass a current through it. Let's see what the student suggests. Suggests that there are several ways of transferring energy. Okay, transferring energy to a small stationary block of iron on a smooth table. You heat it because it's conduction. You know, it's a metal. Iron is a metal. So heat will be transferred by conduction. You know, there are 3 methods of heat transfer in thermophysics: conduction, convection, and radiation. Okay, so you heat it because it's a metal. 1, that's true. Shine light on it, yes, that's true. 3, pass a current through it, yes, that's true. So all 3, I think all 3 methods are correct. Which suggestions are correct? 1 and 2 only, 1 and 3 only, 2 and 3, 1, 2, 3. I think it's 1, 2, 3. Okay, now we go to question 11. An engine produced 240 kilogram, sorry, not kilogram. An engine produces 240 kilojoules of energy in 2 minutes. Oh, energy is good. So if you want power, what is the power output of the engine? What's the power? Power is energy over time, or work done over time. But you must know kilojoule, what it means. Okay? So power is energy. Since they are talking about energy, you say energy over time. If they are talking about work done, you say work done over time. Okay? So the output energy will be what? In 2 minutes. So this time must be converted to seconds. So that's one thing you should take note in the exam. When they give you time in minutes, you must, in hours or minutes, you must convert to seconds. 2 minutes means 2 times 60. Okay, because 1 minute equals to 60 seconds. 2 minutes will be 2 times 60, which gives us 120 seconds. So this is where some students fail, conversions and all of these things. So the time is 120 seconds. the energy must be converted to joule. So even if you leave it clean, it's still part of okay. So meaning you add 3 zeros to it. Okay, 240, you put 3 zeros, meaning multiply by 1000. So you say 240 0 0 0 0 3 0 to it. That's the meaning of joule. Changing from kilojoule to joule. Divide by 120. If you divide by 120, what do you get? So first, you can just say this 0 cancel this 0. 12 go here 1, 12 go here 2. So now we have 2 0 0 0 1 2 3. That's 2000. So we get 2000 watts. 2000 watts, which you can convert to kilowatt if there is no watt. 2000 watts. That's the work done. And sorry, that's the power, output power of the engine. So which is 2 kilowatts. Okay, 2000 watts is equivalent to 2 kilowatts. So we look for option that either has watt or kilowatt, 2 or 2000. Oh, A. So our answer is A. Is that so? The output, we are looking for the output. Yes. Our answer is A. Is that okay? Now let's go to question 12. Quickly. Question 12, we're saying that a book has a mass of 400 grams. The surface of the book in contact with a table has a dimension of 0.1 by 0. So you can calculate the area. The surface has a dimension of 0.1 and 0.2. This is the surface. Here is 0.1, so we can calculate the area. 0.1, here is 0.2. So you can calculate the area of the surface. Okay? So by multiplying 0.1 times 0.2. The gravitational field strength is 10. G is 10. So we have G equal to 10. We have area. So let's know what, because you must know what is given to you. You have area, so that you know what you are looking for. Area, what's the value of area? Okay. Now, you say what is the pressure? Area is 0.02 because 0.1 times 0.2 is 0.02. Is it centimeter? Meter square. So get meter square. G is 10. What's the pressure exactly on the table? So pressure is force or weight over area. Pressure is force or weight over area. So we can say weight over area. So what's the weight? The weight of the object. The weight is, they give you mass. This mass we have to convert to what? Gram. Sorry, we have to convert to kilogram. So to convert to kilogram, you change it to you say 400 divided by 1000 to change it to kilogram. That will give you 0.4, if I'm not mistaken. 400 divided by 1000 will give you 0.4, right? So that's 0.4 kilogram. That's the mass of the object. So remember, to calculate weight, you must say weight is what? Mass times gravity, mg. Weight is mg over the area in order to get pressure. If you want to get pressure, you divide by weight, divide by area. So this becomes 0.4 times 10. 0.4 kg times 10, that would be 4. Times 10, all divided by the area, which is 0.02. All divided by the area, which is 0.02. So 4 divided by 0.02, what do we get? We get 200. 4 divided by 0.02, we get 200 Newton per meter square. Newton per meter square. So we look for the option that has this answer. A, no. B, no. C, no. D. Okay, D. So 200 Newton per meter. So we go to the next question because time is not it's not our friend. So let's take a look at question 13. Question 13 says, the diagram shows a mercury barometer. At which point is the pressure greater than the atmospheric pressure? You know, atmospheric pressure is acting over the surface. Atmospheric pressure is acting over the surface. Okay, and atmospheric pressure, when you are calculating the atmospheric pressure or the pressure in this barometer, we use the height from the surface, from this surface to this place. We use it as our height. From here to here, we use it as the height, the h, that we use in our pressure calculation. We use this as the height of the liquid that is being displayed here. Remember, pressure is equal to rho GH. Okay, but this is not what they want us to do. They just want to ask us a question. Okay, this is a density times gravity times height. It will give you the pressure. You're able to calculate the pressure. But you say, at what point is the pressure greater than the atmospheric pressure? Okay, at what point will the pressure be greater than the atmospheric pressure? I think pressure at the bottom, right? Not at this point. Obviously not here, because to be greater than atmospheric pressure, because atmospheric pressure is acting here on this surface. So the pressure below the water in the basin, that's where. So we go for D. Okay, this question will go for D. So that's when the pressure is greater than the atmospheric pressure. So we go to question 14. Question number 14. Question number 14, we say the table gives information about molecules. Now, which row describes a gas? Force between molecules. Strong. No, force between molecules is never strong. So I think anyone that has strong is already wrong. Force between molecules are not strong. So we consider C and D. Consider, say it's negligible, means very weak. Far apart, close together, far apart. So we'll go for C as an answer for this question. So we move to question number 15. This is Brownian motion. This one is, you remember Brownian motion? This is Brownian motion. It's a very small polygrains are suspended in water. A bright light shines from the side. See the bright line? It's shining on the polygrains that are suspended in water. Now, when looked at through the microscope, small specks of light are seen to be moving randomly. Excuse me. Small specks of light are seen to be moving zigzag, 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 random, colliding with themselves, colliding with the walls of the container in a jerky manner, in a zigzag manner. Okay? Now, what is the moving speck of light? What is the moving speck of light? You say polygrains be hit by other polygrains. No. Polygrains be hit by water molecule. Correct. So we go for this. It's not water. It's about polygrain. Okay, we move to question 6 to save time. Now, why are small gaps left between the metal rails of a railway track? Why are small gaps left between the metal rail of railway track? To allow for expansion, yes. But we will see, because I know they will write more than one expansion. To allow for expansion of the rail on a hot day. Super correct. But let's see. To allow for contraction, no. To allow for expansion of the rail on a cold day, no. So the answer is A. To allow for expansion of the rail on a hot day. We go to question 17. 17 is calculation. You know, this calculation, they take a little bit of time, right? They take a little bit of time. Now let's take a look. We say a block of metal absorbs 200 joules of thermal energy. The temperature of the block, this is the energy, 200 joules. So our energy has been given to us. So they probably going to ask us something else. 2,000 joules, not 200. 2,000 joules of energy. So you remember this energy formula for heat capacity or specific capacity? Energy equals to MC specific capacity times delta T. Delta T means change in temperature. Okay, so this is the formula so it depends on what they want us to calculate. The temperature of the block rises from 10 to 20. So change in temperature will be 20 minus 10, which is 10. So delta T, you always know your parameters, okay? Delta T is T2 minus T1. T2 minus T1, which gives us 20 minus 10, which is 10, right? 20 minus 10, which is equal to 10. So our change in temperature is 10 degrees Celsius. Okay, we resolve that. The mass of the block is 2 kg, so you write your M. You read the temperature, you write your M, right? M is what? Your mass is what? 2 kg. 2 kg. Now, You say, what is the specific capacity of the metal? What is the specific heat capacity? So you're going to make this one the subject, this one. You're going to make it the subject. You're going to make this one the subject of formula, this one. This small c of x, cx. You're going to make it the subject. So to make it the subject, cx is equal to the energy divided by energy on the right over mass and delta t, mass and delta t. So this is what all you just need to do, and you get your answer. So this gives us the energy is 2,000, so you write 2,000 here, 2,000 here, divide by the mass, which is 2 times 10. 2 times 10 is 20, right? 2 times 10 is 20. Delta T is 10. Remember, we've done that already. Delta T, change the temperature is 20. So you get, change the temperature is 10. So you say 2,000 divided by 20. 2,000 divided by 20. That will give you 100, right? That will give us 100. So we look for the option B. Option B. So our answer here is B. Our answer here is B. Okay? So our answer here is B. So we get B as our answer. The unit will be joule because it's joule over joule kilogram per degree Celsius. Okay, we go to question 18. Quickly. 18 says, question 18 says, which statements about boiling and evaporation is correct? Say, boiling requires a supply of thermal energy, but evaporation does not. No, they both require energy. So A is wrong. B is evaporation takes place at the surface of the liquid, but boiling takes place throughout it. Yes, this is super correct. But we have to read all this. Say, when water boils in a kettle, its temperature decreases. No, temperature rises. When water evaporates, its temperature increases. No, if you evaporate, temperature decreases. So B is the absolute answer. So we go to question 90 as fast as we can. We go to question 90 as quickly as possible. Question 90 says, a metal rod is heated at end X. You hit a metal rod at end X. Here, you are hitting it from here. So why does end Y of the metal rod becomes hot? Oh, heat is transferred by conduction, right? So you say energy is transferred from end X of the rod to end Y by vibration of positive ion. That's correct. Metals, they are positive by vibration of positive ion and by movement of electron. Yes, vibration of the positive ion and movement of electron. A is correct, right? Should we read the rest or we move on? I think this is absolute. We'll go on. This is absolute. Now let's go to question 20 for the sake of time. We say two square sheets of metal P and Q are heated. Two square sheets of metal P and Q are heated to the same temperature. The metal sheets are shown. This one looks black, right? And this looks shiny, something like that. But this smaller because they are square, right? So which means if here is 20, here is 20. So you can easily find the area or find whatever. Now sheet Q, this is Q, the shiny one. Sheet Q is emitting more radiation than sheet P. More radiation, maybe because of the surface area. Which statements explain this? Which statement explain this? Dull black surfaces are better conductors of radiation. I don't think that's it. Dull black surfaces are better emitters of radiation. The surface area of Q is larger than that of P. Yeah, this is obviously the reason why this is emitting more heat. Surface area of this is way larger. If they were equal in surface area, this one would have emit more. So we go for C. I think we go for option C as our answer. Is that okay? We go for option C as our answer. Now let's go to 21. Question 21. A water wave passes into a region where the wave travels more slowly. Now, as it passes into this slow region, what happens to the frequency and what happens to the wavelength of the wave? What happens to the frequency and what happens to the wavelength of the wave? Frequency will not change because even if you are moving from a denser to less dense, the frequency will remain same, but the wavelength will change. So is it moving from less dense to a denser one? That will determine. If it's moving from a less dense to a denser one, the frequency will decrease. Now let's see. As it passes from a slow region So as water wave passes into a region where the wavelength travels more frequently, or it passes to a region where the wavelength travels more frequently. As it passes into a slower region, what happens to the frequency and what happens? If it enters a slower, the wavelength will decrease, obviously. Wavelength will decrease, but the frequency is always same. So we go with C. Now let's go to question 22. 22 might be a little bit of calculation, and we see how that takes us. Light traveling at a speed of, so this speed of light, VA. Speed of light, we can say VA, speed in air. Okay, is a constant value. 3 times 10 to the power of 8. 3 times 10 to the power of 8. 3 times 10 to the power of 8 meter per second. And strikes the surface of a glass block and undergoes a refraction, and it enters the block. It strikes it, they've given us angle of incidence, and they've given us angle of refraction. Now the incident, the diagram shows a ray of light. The diagram shows a ray of this light before and after it enters the block. Now what is the speed? What's the speed of light in the glass? First, we have to calculate the refractive index, because speed of refractive index is equal to the speed in air over speed in a medium. Speed in air, this is V, okay, to signify speed. Speed in air over speed in the glass. Over speed in the glass. So you cannot do this if you don't know the refractive index, because you cannot find the speed in the glass, because they're asking us for the speed of light in the glass. You cannot do that if you don't calculate the refractive index of the glass. And you can use you can calculate the refractive index by using since it's coming from a less dense medium, air, to a denser medium, glass. So refractive index will be the sine I, sine of the incident angle, over sine of the refracted angle. But if it was coming from a denser one to a less dense, it would have been sine from here over sine over this one. Okay, so this is sine 55 over sine 33 over sine 33 over sine 33. So we have to solve this and see what do we get overall. What do we get? 0. What? For the top one, right? For the top one, we get 0.8 what? 0.819. 0.819. We can stop there. Or 8192. 0.8192. Then for the sine 33, what do we get? Sine 33 will be getting like 0.5 something. 5446. 0.5446. So we divide the numerator by denominator, we get our refractive index to be, what's our refractive index? You get your refractive index to be 1.6 or 1.7 approximately. It looks like 1.7 approximately. Okay? It's usually from 1.5 to 1.6 or 1.7. Okay. See, we're on track. So you make the V glass the subject, because you are calculating speed in the glass. Make it the subject. First, you cross multiply. So you have refractive index. You come here, you bring this formula, refractive index, multiply by the speed in a glass. The speed in glass, Vg, is equals to speed in air. Equals to speed in air. So to find the Vg, the speed in a glass, to find the speed Vg, which is speed in a glass, is this 3 times 10, which is speed in air, to the power of 8, divided by the refractive index, times 10 to the power of 8, over 1.7. So what you can just do, just say 3 divided by 1.7. 3 divided by 1.7, what do you get? 3 divided by 1.7, everything will be 1.8, approximately 1.8 times 10 to the power of 8. So everything will be approximately 1.8 So this will be, you see, the speed will slow down from 3 times 10 to the power of 8 to 1.8 times 10 to the power of 8, because the object has moved from less dense medium to a denser medium. So when you go into a denser medium, your speed will slow down. Okay, your speed will slow down. So our answer will be A, right? Our answer will be, is it A? Our answer is B, because this is supposed to approximately 2 to the nearest whole number. 1.99. Okay, yeah. When we divide, we get 1.99. Sorry. So 1.99 is approximately 2. Sorry, that's a mistake. This is 1.99. 1.99 is called 2. It's 2. So you say 2 times 10 to the power of 8. So our answer is B. Okay, be careful when you do division in the exam. If not, you get something you know how to do, you still fail it, which is the worst thing that will happen to anybody. If you fail what you know, then the chance of you passing the exam is almost close to 0. Okay, you must be able to harness what you know very well. Now let's move on to question 23. For question 23, let's quickly go through question 23. It said the diagram shows a narrow beam of light incident on a glass air boundary. Some of the light emerges along the surface of the glass and some are reflected back into the glass. Some emerge at the surface, like total internal reflection. You know, this is the optically denser medium. When anything is coming from optically denser medium, here, the angle of incidence for which this happens is called the critical angle. This will be called the critical angle. The angle of incidence for which some of the ray of light start to move at the boundary between the two media is called the critical angle. Okay? You say, which row is correct? Which row is correct? This is an example of total internal reflection. No, it's not an example of total internal reflection because some of the rays are moving at the boundary. It's not all the ray that goes inside. Some are moving at the boundary. So they are not totally internally reflected. Okay, so A, right? Just a minute. So this is an example of total internal reflection. No. So no is correct because it's not a total internal reflection. So these two options, we will consider them A and B. Definitely C and D will be wrong because it says yes. Is this a total internal reflection? No. This is not a total internal reflection. So C and D is wrong for saying yes. So it's no. We consider the angle theta is the critical angle. Yes, I already mentioned that. This is a critical angle. Anyone that says yeah, that's the answer. So A is the answer. This angle theta is a critical angle. Why? Why is it a critical angle? So when a ray of light is coming from an optically denser medium into a less dense medium, the angle of incidence for which some of the ray will be refracted along the boundary between the glass and air is called the critical angle. It's called the critical angle. The angle of incidence, note what you call the incident angle, for which some of the refracted ray will move at the boundary, will be 90 degrees to the normal. Because if you draw this angle, it will be 90 degrees to the normal. This is the normal line. This one is the normal line. For which the refracted ray is 90 degrees to the normal. It's called, this angle of incidence will be called critical angle. This is called critical angle. So A is the answer. We go to question 24. Question 24 is about length. Okay, it's a question on length. Now, an object is placed in front of a thin converging lens. An object is, look at the object in front of it. You know there are three rays for drawing an image in a lens, in a convex lens. Okay, in a convex lens. But two of these rays are sufficient to form the image. Okay, but they may ask us, you refract this one to pass through the principal focus, and then this one that passed through this optical center will continue to go undeviated. This ray will continue to go undeviated. Okay, in exam you can use a ruler to draw a straight line. Why this one will come till they meet? Will come like this till these two rays meet. Okay, till they meet. And where they meet, that's where image is formed. Okay, where they meet, that's where the image is formed. Image will be formed here. Although we've not finished reading the question, we don't know what the question is going to ask us, but I'm just showing you this type of thing, how it works, how it plays out. Okay, so you say an image of object is formed on a screen to the right of the lens. To the right on the, how does this image compare with the object? How does the image compare to the object? Right? Is inverted? That's true. And it's larger. The image will be larger, this eye. Okay, if you use ruler, you will see it clearly. This one is longer than this. It's longer than this. So the image is larger and inverted. You can see it's inverted, meaning it's laterally inverted. It's turned upside down. Okay, so larger and same way up is wrong. It's not same way up. Okay, smaller and inverted, no, it's not smaller. Smaller and same way up, no, it's wrong. So the most correct one is larger and inverted. So we go to question 25. We go to question 25. Let's see how fast we can do this. A remote control vehicle is traveling on the surface of the planet. The vehicle senses an obstacle ahead. It sends a radio message to the control room from where it is being controlled. And the control room is 2.4 times 10 to the power 6 kilometers away from the vehicle. Now the control room sends a message back to the vehicle telling it to stop. What is the minimum time that elapses between the vehicle sensing the obstacle and receiving the message back from the control room? This is a bit long. You have to calculate the radio. First of all, speed is distance over time. Okay, if you cross multiply, you say time is distance over speed. Distance over speed. Okay, this distance, let's see, is it a circular motion? A remote control vehicle is traveling on the surface of a planet. On the surface of a planet. Planet is circular, right? It's traveling on the surface, okay, of a planet. The vehicle senses an obstacle ahead. It sends a radio message to the control room, from where it is being controlled. Now the control room is 2.4 times 30 kilometers away from the vehicle. The control room sends a message back to the vehicle telling it to stop. That's 2D. The distance is two-way, 2D. So here will be 2D. Tell it to stop. Now what's the minimum time that elapses between the vehicle sensing the object and receiving the message back from the control room? So we have our distance. Okay. What about the speed? Any information on the speed? We have the distance given to us. And this distance, if it's circular, you can say 2 pi r radius. But I think no need for this. And then the speed, information was not given to us. What's the minimum time? The minimum time that elapsed between the vehicle sensing the obstacle and receiving the message back from the controller. 2D, sending it. So we multiply this by 2, we get 48 times 10 to the power of 6. Right? 4.8 times 10 to the power of 6. Divide by 2.4, that you will get 2 times 8 times. I think the answer will be 60 seconds. Okay, to save time, we'll come back. If we have time, we'll come back to solve it. I think the answer will be to show the solving. Okay, we'll come back to show the service because this one will take time away from us. A sound wave is traveling outward from a loudspeaker in a surrounding air. Here are three statements. We have three statements from the sound wave, right? Now let's take a look at these statements. Let's take a look at this statement. The first one is that the air pressure is lower at a rarefaction. The air pressure is lower at rarefaction compared to the undisturbed air. You know we have compression, rarefaction. Compression, rarefaction. Now the density of the air is less. The density of air is less at a compression compared to the undisturbed air. Then the distance from a compression to a rarefaction equals half the wavelength. Now, which statement about sound waves is correct? Which statement about sound wave is correct? First, let's take a look at them again. The air pressure is lower at a rarefaction. Yes, this is correct, right? Compared to the undisturbed air. Okay, now the density of the air is less at the compression. No. The distance from a compression to a rarefaction equals half the wavelength. Yes. So I think 1 and 3 is correct for this question. The distance, you know compression, rarefaction? Compression. Then you have rarefaction. Then you have compression again. You've done this other longitudinal waves. We studied longitudinal waves. Then we have rarefaction. We have compression, we have rarefaction. Okay, so the distance, to save time, the distance from a compression to a rarefaction equals half a wavelength. From a compression, the distance from here to rarefaction is half of the wavelength. So the 3 is correct. So we have 1 and 3 both correct. So we move on to the next question. Question number 27. The sound from a loudspeaker must pass through two materials to reach a microphone. The sound, this is a loudspeaker. The sound from a loudspeaker must pass through two materials to reach a microphone. This is material 1, this is material 2. This is where the microphone is. Okay? Which combination of material Which combination of materials give the shortest time for the sound to reach the microphone? Which combination of material give the shortest time for the sound to reach the microphone? Or combination of material. Air and hydrogen, no. Right? Sound travel fastest in solid, followed by liquid, then the gas is the least. So this is gas. It cannot be the shortest time. So this is also not correct. So A and B not correct. We look for the C. I think C is the most correct one, because sound travel fastest in air solid than in any other material. So we go to question 28. Question 28. We say diagram 1 shows a small compass needle with its pole marked. It is not near any magnetic material. Diagram 2 shows a bar magnet with its pole marked. The compass needle is placed at point P. The compass needle is placed at point P. Now this is diagram 1, this is diagram 2. In which direction will the north pole of the compass needle point? In which direction will the north point? Right? Which direction will it point? To the right, right? Because left is already north. North and north, they cannot point towards each other. This compass will point to this direction, to the left. You know why? Because this north has to be this way. because the magnet, the knot is already on the right. So knot cannot be towards each other. So this one cannot turn to this side. Cannot turn to this side. So it has to turn in the opposite direction. So it will point towards the right. Okay? This is called right in this context. Okay? Okay, now let's move to question 29. Let's move to question. A student rubs a plastic rod with a cloth. Okay, this is electrostatic. A student rubs a plastic rod with a cloth. The rod becomes positively charged. The rod becomes positively charged. A student rubs a plastic rod with a cloth. The rod becomes positively charged. Right? Now, what happens to the rod? It has gained electron? No. It has gained proton? No. It has lost electron. Right? Because you become positively charged when you lose electron, like metals, When they lose electron, they become positively charged. So it has lost electron. That's why it's positively charged. Question 30. Question 30 is, say, an isolated metal sphere is positively charged. This one is positively charged. Now it's then brought near to another isolated metal sphere that is neutral. Okay, that is neutral. Now what happens to the charges on the neutral sphere as the positively charged sphere is brought near it? You bring the positively charged here, so all the negative will kind of align on this side, right? Will be attracted to this way. And the positive will be rearranged to this other side. The positive will be rearranged to this other side, right? And before you earth it, right? Now let's read the option. Some positive charges move to the left. No, positive do not move to the left. Some positive charges move to the left and some negative charges move to the right. No. Some positive charges move to the right and some negative charges move to the left. Not some. When they use the word some, it will not be correct. It will be all. Okay? All. Some positive charges move to the right, while some no. The positive charges do not move. Okay, they remain wherever they are. But the negative one, they will all spread out like this. But some negative charges move to the left. I think this one is more correct, right? Question 30. D. This one is more correct based on all the options that we have. Okay, question 31. Say which statement about the resistance of a metal wire is correct? Which statement about the resistance of a metal wire is correct? Now the resistance is directly proportional to its length. Resistance, you say, is directly proportional to the length. That's true. And it's inversely proportional to area. You know that, right? You say the resistance is directly proportional to length and directly proportional to its cross-section. Wrong. Because area is not direct. Area diameter is inverse. Inverse proportionality. The resistance is directly proportional to the length and inversely proportional to its cross-sectional area. Correct. So I think this is the correct. The resistance is inversely proportional. No. Resistance is inversely proportional to length. No. These and these are outrightly wrong. Resistance is directly proportional to length and inversely proportional to cross-sectional area. So we'll move to question 32. Question 32. This is a potential divider. Okay. So the circuit diagram shows a light-dependent resistor. Shows a light-dependent resistors in a potential divider. A voltmeter is connected across the LDR, light-dependent resistor. A voltmeter is connected across the light-dependent resistor. This is the light-dependent resistor. It's showing you the arrow that light is shining on this resistor. That's why we call it LDR, light-dependent resistor. So this one is called light-dependent resistor, LDR. Is that okay? Which row shows the resistance of LDR and the potential difference the potential difference shown on the voltmeter at a specific light level. At a specific light level. So which row shows? It's a which row? We're going to look at the light level. Okay. We're going to look at the light level, and we also look at the resistance of LDR and the distance. So the light level is bright when the resistance of LDR is low and the potential, the voltage is high. You know, PD means voltage. This is wrong. This is not true. You say the light level, when it's bright, the resistance will be high. Resistance will be high, and the voltage will be low. That's wrong. If light is bright, right? You say this one is high, then this one will be the other way around. Let's see, light, when the light is dim, the resistance will be high. Yes, because these are inversely proportional. When light is dim, resistance is high. When light is bright, resistance is low. Here should have been low. Okay, when light is dim, resistance is high, and then voltage will be high. But if this one I say bright, low, low, this one would have been correct. A would have been correct. So when light is dim, when the light is dim, resistance is high. If resistance is high, the voltage is high. Okay, because voltage is directly proportional to resistance. V equal to I arrow. V equal to I arrow. Okay, so the voltage will be high. So C is the most correct one. We go to the next question, question 33, as fast as we can. Okay, question 33. I think now they removed the logic gate, right? But let's just go. I don't know if they removed it or it's still there. But let's see what it is. Is it three NAND gate? NAND gate means, you know, this is AND. Once you put a small circle in front of AND gate, it becomes a NAND. So 3 NAND gates are connected in a single chip, as shown. This is input 1, input 2, and the whole chip behaves as a single logic gate. Which type of logic gate does the chip act as? Okay, in order to get this one easily, you draw the truth table. You draw the truth table, the outcome from the truth table. So if you do a NAD, NAD means opposite of AND. So which becomes OR. This is like OR. This is like OR. And this will become like OR. So the output behavior will be OR gate. So we look for OR gate. Because the meaning of NAD means the converse of AND gate. AND gate. This and this must be bright in order for the bulb to light. Switch 1 and switch 2 must be on in order for the bulb to work. That's AND gate. But OR gate means this or this. Either you on this switch or you on this switch, the light will on. So OR gate is NAD is opposite of AND. And the opposite of AND becomes OR gate. So it results to an OR gate without solving anything. Okay, now we go to question 34. Question 34 is on magnetism. A solenoid is connected to a very sensitive ammeter. A rod is inserted into one end of the solenoid. Now the ammeter shows that there is a small electric field. There is a small electric current in the solenoid while the rod is moving. Now which rod is being inserted? Which rod is being inserted? Right? Let's go through it again. A solenoid is connected to a very sensitive ammeter. This is a solenoid. Is connected to a sensitive ammeter. Could be a galvanometer, a very sensitive ammeter. A rod is inserted into one end of the solenoid. So you put a rod through this space into the solenoid. No magnetic field will be produced or current will be generated. The ammeter shows that there is a small electric current. This ammeter shows there is a small electric current in the solenoid while the rod is moving. Now which rod is being inserted? Which rod? Now let's see. A heated copper rod, no. A magnetized steel rod, yes. But for solenoid, we use steel rod. If you are using electromagnet, you use iron. But this one we use steel. Steel is able to go through magnetism, right? So we say a magnetized steel rod. So I think B is the answer. It's not a liner, it's not a uranium. These are completely far from it. Okay, now let's go to question 35. Question 35. It says the diagram shows an electric generator with the coil in a vertical position. The coil is vertical now. Look, it's no more horizontal. It's rotating. This one is rotating. This coil arrangement is rotating. These are the slip ring commutator. These are the carbon brushes. The carbon brushes are connected to the slip ring commutator. And the slip ring commutator rotates with the coil's rotation. Which role describes the generator? Which role describes the generator? Say the generator produces an AC. Of course, any DC is wrong. Generator is AC, motor is DC. Generator is what? AC. So our answer is A and B. So we now check which one. The coil is horizontal. The coil is vertical. Of course, the coil has been said to be vertical. Is that not what they said? Look at it. The coils are vertical. These two cheap. Okay, the coils are vertical. So the answer is B. The coil is vertical. Coil. This one. They're vertical. Horizontal one would have looked like this. The coil would have looked like a rectangle like this. This is horizontal one. Vertical one will look like this one. Okay, so we move to the next question. Question 36. We move to question 36. 36 is a transformer. 36 is a transformer. We have a video on transformer, we have a video on generator, right? We have a video, so you can go to IGCSE Academy and watch the video on transformer, generator, transmission lines, and so on and so forth. Even electric motor, I guess. If we've not done for electric motor, that will be coming soon. Now, the diagram shows a transformer. There are 200, transformer is, you can start with NS over NP. If you put S on top, you make it throughout. Over NP is equal to VS. You cannot now write, you can write VP because you started with S, secondary side. So you must write VS over VP if you want to find any of this in the transformer over VP. Okay? But if the transformer is 100% efficient, we have another formula for it. Now, it's a diagram shows a transformer. There are 460 turns on the primary. That's NP. 460. So I have here at the bottom 460. I have 460 turns on the primary and 24 turns on the secondary. So on top here, I have 24 on top on the secondary. Okay, this is equal to, what is the voltage? They will give us the voltage, at least one of them. The primary voltage 230. So VP, they did give us VS. They will tell us to calculate VS. What's the secondary voltage? That's VS. So you are making VS the subject. VS over the primary voltage, which is 230. Put 230 here. So you cross multiply and you get your answer. We cross multiply, we get 24 times 230. If you cross multiply, you get 24 times 230. 24 times 230. That will be equal to your VS times 460. So I can just go ahead to divide by my 460. Okay? At least we are at this stage, you should be matured enough. You can write times 460 here, then you make VS the subject, and then you divide by 460. So 24 times 230, whatever you get, divide by 460. Divide by 460. What do we get? Our VS will be equal to what? Is it 12? Yes, our VS equals to 12 volts. Our VS equal to 12 volts. So we look for 12. Okay, B. So our answer is B for 36. So let's go to 37. 37. The charge on a proton is E. The charge on a proton is E. What is the charge on an electron and what is the charge on a neutron. Neutron do not have a charge. This one is 0. If the charge on a proton is E, the charge on the electron will be minus E. If proton is E, the charge on the electron will be negative charge. Neutron do not have a charge. So what is our answer? D, right? So our answer is D. We move on to the next one. Question 38. 38. 4 students are asked to comment on the processes of nuclear fission and nuclear fusion. Their comments are recorded in the table. Now, which role is correct? Fission and fusion. Fusion is joining. This is splitting. Fission is splitting. Okay? Splitting of nuclei, radioactive nuclei. This one is splitting. Why this is joining together to make a bigger thing, this joining. Okay, I just use a keyword to let you know what you're looking for. Okay, so now let's see. Energy is absorbed. No, in nuclear fission, energy is released because it's splitting. Energy is released. A large unstable, this one is already wrong, right? We go to 2. A large unstable nuclear split. A large unstable nuclear split, okay. Energy is absorbed. No, here, energy is released. So because of this one is not correct. 2 light nuclear join. No, this is not joining. C is not joining. Fission is not joining, splitting. Energy is released, yes. Energy is released. 2 nuclei join together. Yes, this is joining. So this is the answer. In fission, nuclear fission, energy is released, and in nuclear fusion, 2 nuclear these join together. So our answer is D. So we go to 39. I think you're already familiar with all these small things. We did this a lot. We have a video on this, right? We have a video on this. So you can go to waidusmacademy YouTube page and watch the video and subscribe to our page. Question 39. Radon is 21986, decays by emitting an alpha particle. If you emit alpha particle, you go to -4 from here. You go to -4, and you go to -2 from here to form the next thing. So this one will be 86 minus 2, you get 84. So whatever you're going to get, the atomic number will be 84, and the mass number will be 215. If you emit an alpha particle. Okay, if you emit alpha, so you have to look for which one has this A, right? So polonium, you get polonium, which is 250 and 84. So that's it. Now we go to the last one, which is radioactivity. Okay, we say the graph shows activity of radioactive salts over a period of time. Activity of radioactive salts over a period of time. Okay, what is the half-life? Okay, so since the activity starts from 120, you go to half of 120. Half of 120 is 60. Trace 60 to the graph and trace it to the minute column. Trace it down to the minute. So it's 2 minutes. So our answer is B, 2 minutes. 2 minutes. So it's easy. So with this, we've come to the end of our today's class. Thank you for joining us.